So you have your PowerPoint in front of you. You need to have a calculator with you because we're going to be working some problems. And I'm not planning on going over any of this in class on the next day, Thursday. So you want to make sure that you understand this pretty well before you leave this PowerPoint. And this may get split over a couple of different video sessions, just depending on how long it takes me. So this is all chapter 27 of your book, but it's a very abbreviated version of chapter 27 in your book. So first of all, we need to just look at the basic model of the atom. And we have a nucleus in the center, which you are aware of. So there's our nucleus, has protons, neutrons. Right now, we're not going to be dealing with the nucleus. We're going to look at the electrons that are on the outside of the Okay, I'm sorry. For the pause there, Mr. Mazinski came in to see me, so I had to work with him for a second. All right, so we have the nucleus in the center, which we're not going to be looking at. Let me go back. And the electrons on the outside, that's what we're going to be looking at for now, is what's going on with these electrons. So if you remember from chemistry class, the electrons exist in different orbitals around the nucleus. And the lowest orbital, this one here, those electrons, of which there are typically 2, those electrons have the least amount of energy. So this close to the nucleus orbital is least energy. And although they don't stay perfectly at that location around there, but you would say typically they're going to be 2 electrons, or up to 2 electrons, that have the least amount of energy. And then as the orbitals get higher away from the nucleus, they gain more and more energy. So the electrons that are in this next orbital up would have more energy. And then if you had another orbital beyond that, they would have even more energy. So in terms of the actual energy of the electrons, the kinetic energy of the electrons, these guys on the inside would be moving slowest because they have the least energy, and the guys on the outside, if there were electrons out here, they would be moving fastest because they have the most energy. So that's the basic model. This is the Bohr model of the atom. Now the electrons are able to move around between these energy levels. So if this electron, for example, wanted to jump up to a higher energy level, he doesn't have enough energy right now to get there. But if somehow he was given some energy, there's different ways you can do this, but if he was somehow given some extra energy, just the right amount that he needed, he could actually jump up to this energy level if he was given just the right amount. Once he got up there, he may not like it there. He may see this open space, or another electron even might see this now as an open space, and that electron might jump down. But again, he can't jump down without shedding off his excess energy, because he has too much energy up in this upper level to jump down to the lower level without shedding off whatever is excess. Now, how does this happen? The giving of energy happens sometimes. You can, well, there's different ways you can do this. You could illuminate the atom with a light, and if the electron absorbed the light, it could jump up, and then when it jumps back down, it could give off the excess energy in the form of a photon, a type of light. Or you could give the atom energy by charging it with electricity, and that might cause the electron to jump up and jump back down. Or you could heat the atom, and that might cause the electrons to gain energy, so they jump up and then they jump back down and they give off photons. These photons could be in the visible range, and it might be something we could see. So it is possible to make an atom get into an excited state, meaning that the electrons jump up to higher levels and then jump back down. And you might be able to see that atom glowing, or you might be able to see that atom give off light. And so that's something that happens with lasers. Lasers work this way, where the electrons jump up to higher levels and then jump back down and give off photons of light. It works when you excite gases in a neon light, for example, and the gas glows and gives off light. So these are all different times when you might see electrons jumping between energy levels. Now this electron right here, he doesn't have to just jump up one level. He could possibly jump up 2 levels or even more. So he might jump, if you give him enough energy, he might actually choose to jump all the way up here. And then when he jumps back down, he could either jump like this, or he could make one full jump. Each one of these jumping between energy levels corresponds to a different amount of energy absorbed or given off. The amount of energy for the energy levels is going to depend on the atom and how close it is and what orbital it is, and we'll learn how to figure all that out in the future shortly. But you should at least know that there are different energy levels, and we label those with the letter N. So the lowest energy level is the N equals 1. It's also called the ground state. That's the lowest possible energy level. And then N equals 2 is the one up from that. And then this would be N equals 3, and then they would go from there. As many energy levels as that atom happens to have. And those are all your various energy levels. All right. So what do we see when we're looking at an atom that's been excited? Well, when you take an atom and you excite it by either heating it up or electrifying it, like putting electricity through it, those atoms, those electrons, when they jump between your energy levels and then jump back down, they give off photons of light, and those photons have very discrete wavelengths. And so you would see, if you were looking at that atom get excited, you would see specific photons of light that correspond to all the various jumps in energy level. Each one of these is a different photon of light. So this might be one photon. This would be a different wavelength right here. And that one would correspond to another wavelength right there. And this one would even correspond to another wavelength right there. So each one of these wavelengths you would be able to see. And if they were visible, you would see them as actual, they would show up as stripes. So if you looked through a machine called a spectroscope, which I imagine you've seen before, if not, we'll see in class tomorrow, you would actually see very discrete colors of light corresponding to the various wavelengths that are given off by the different jumps between the energy levels. And that is something that is unique for each element. So hydrogen has very specific wavelengths. This one's mercury, that has very specific wavelengths. Neon has very specific wavelengths. So each one of these elements has very specific wavelengths given off by the jumps and the energy levels for that particular element. So how does that end up working? So this is an example. This is hydrogen. This is the emission spectrum for hydrogen. There are 4 lines that are given in the visible range, or 5, pardon me. 5 lines given that are actually visible. There are a lot more that are given off that we can't see. But the 5 we can see are a red, a teal, a blue, and 2 purple colored lines when we look at hydrogen. So what those represents different jumps in energy, electrons between different energy levels. So this is the way this is drawn out right now, and this is how we typically draw them. The bottom line represents the N equals 1 ground state. The second line up will be the N equals 2, N equals 3, and it would go up like that. You can see that they're kind of drawn so they're getting closer together because there's less and less energy difference between the various ground states. The N equals infinity ground state, the N equals infinity state is a free electron. So if I take an electron and I move it from the N equals 1 and I give it enough energy to get out to N equals infinity, that means that electron is now broken free from the atom. And we can say that that atom is now ionized. That's the word we use, meaning that the atom has now lost an electron. And so it has become an ion and has a charge now. So if you want to free an electron out of here, and if it's in the N equals 1 state, you have to give it enough energy to get it all the way out of the atom. How much energy that is depends on the atom itself. If this is a hydrogen atom, which it is, the amount of energy of the electron in the ground state is negative 13.6 electron volts. Negative because what this means is I would have to put in 13.6 electron volts to get an electron that's down here all the way out of the atom. That's what this means. So an electron that's in this level, in the N equals 2, would need 3.4 electron volts added to it so that if it wanted to ionize, if you wanted to get it completely out of the atom. Now if I only want to make this this one jump up to the next level, I don't have to give it an entire 3.4, I just have to give it the difference between 3.4 and 1.51. So if you do that in your calculator, the difference between that is 1.89. So for that atom, I'd have to add in 1.89 electron volts of energy, and then for that electron, pardon me, and that would cause that electron to jump up to this level right above it. Okay? If I wasn't, let's suppose I wasn't able to give it 1.89, I could only give it 1.7 electron volts. 1.7 electron volts is not going to do anything, because with 1.7 it doesn't have enough to jump up to the next level, so it's not going to go anywhere. So the only ones that are going to actually jump are the ones where you get the exact amount of energy given. Then it'll jump between levels. If it doesn't have enough energy, then it's not going to jump. All right? The same thing is true when it jumps back down. When it jumps back down, it's going to give off the exact amount of energy that is the difference between the levels. So for example, when this electron jumps from the 3 to the 2 level, the amount of energy difference here, what did we say, 1.89? So it's going to give off a photon that has an energy of 1.89 electron volts. That's what's going to be given off when it jumps down. And it just so happens that a photon with this amount of energy has a wavelength that corresponds to about 656 nanometers, which is a red light. So we would see that as a red line on the spectrum, given corresponding to just that wavelength. A photon that jumps from the 4 to the 2 state, if you want to figure out how much that's going to be, you have to do 3.4 minus 0.85, which would be 2.55. So that jump, this green light jump, this one here, corresponds to an energy difference of 2.55 electron volts. And that corresponds to a different wavelength, and that wavelength is more in the teal greenish range, whatever the nanometers is for that wavelength. And then you have the blue, you have the purple, and then this last one is also a purple. They just didn't draw it as purple also. So those 5 jumps are all corresponding to wavelengths that are something that we can see. These jumps over here, called the Lyman series and the Paschen series, those are jumps that also happen, but they're ultraviolet and they're infrared, so we don't see them. They happen, they're happening. That hydrogen, if we excite a hydrogen, it is giving off ultraviolet and it's giving off infrared. We're just not able to see them. So I'm going to stop here, and then we'll pick up how we do our calculations and how we figure out what all these numbers are next.